You ran Gemma 4.12 billion on your 30 GB graphics card yesterday and it worked. That feeling of success is real, but the reality is far more complex than simply getting code to execute without errors. The true bottleneck isn't that you lack enough memory space for the model weights themselves, but a specific architectural ceiling in how data moves through your hardware that forces compromises no one warned you about. By the end of this explanation, you will understand why running a model locally feels different from it actually performing well, and how to choose your stack before hitting those invisible walls. Here is the thing most tutorials skip over when discussing local inference on consumer hardware like the Nvidia RTX 3090. They focus entirely on whether 24 gigabytes of video random access memory can hold the static weights of a 12 billion parameter model, which it easily does in theory. But theoretical capacity tells you nothing about how fast that data moves once the generation starts. The actual constraint is the memory bandwidth ceiling, and this distinction changes everything about your deployment strategy because it dictates whether your system runs or performs. When developers first load these large language models onto consumer GPUs, they often assume that as long as the weights fit in video random access memory, performance will be smooth. This assumption collapses under the weight of real-world inference workloads where context windows expand beyond a few thousand tokens. Recent community reports on Nvidia RTX 3090 hardware reveal a critical bottleneck distinct from raw capacity: inefficient management of key-value cache allocation strategies that forces CPU offloading and drastically throttles throughput. The system does not crash gracefully when it hits this limit. Instead, data transfer between the graphics card's central processing unit becomes the primary latency source rather than compute power. Consider what happens when you attempt to generate text with a sliding attention mechanism designed for high efficiency on Gemma 4 architectures. While the theoretical design suggests optimal performance, real-world benchmarks using inference engines like VLLM and Allama show severe degradation once context windows exceed 3,000 to 4,000 tokens or default key-value cache settings are too aggressive. Users report token generation rates plummeting from expected speeds of over 40 tokens per second down to approximately 19 tokens per second due to the system offloading model layers to central processing unit memory. This creates a scenario where data transfer between graphics card and random access memory becomes the primary latency source rather than compute power, effectively turning your high-speed hardware into a bottlenecked pipeline. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This phenomenon forces practitioners into suboptimal quantization choices that further degrade performance because attempting advanced optimizations like floating-point 8 key-value cache on integer 4 checkpoints triggers runtime errors, while default configurations often restrict usable context to mere thousands of tokens despite 256 gigabytes per second bandwidth potential. The gap between the feeling of success when a model loads and the reality of poor performance is driven by fragmentation, where default allocations, such as 6 gigabytes for key-value cache on consumer cards, force aggressive truncation or quantization that degrades throughput from theoretical peaks to those low speeds due to bandwidth saturation. This means your system might appear functional, but it cannot sustain the data movement required for complex reasoning tasks requiring long context windows without stalling completely. Flash attention instability on RTX 3090 chips creates a hard ceiling at 3,400 token contexts, causing total graphics processing unit stalls with 0% utilization rather than graceful degradation, which breaks agentic workflows requiring long system prompts despite sufficient video random access memory for the weights alone. This is where many engineers get stuck because they can see their hardware specs and assume everything will work smoothly, but the software stack simply cannot handle the data flow required to maintain high token generation rates when pushing beyond default limits. The architectural constraint dictates your entire stack choice by invalidating any narrative that suggests all models fit on consumer hardware regardless of workload demands. When you look at tensor parallelism across dual consumer graphics processing units, it reveals that memory bandwidth is indeed the true bottleneck, even with optimized quantization settings like integer 4, where high utilization settings result in tiny key-value cache sizes around 25,000 tokens because aggregate bandwidth cannot sustain data movement for large context windows, forcing a trade-off between speed and sequence length. This reality means you must choose between low-latency inference with truncated contexts or high-context processing that saturates memory buses, making cloud graphics processing unit selection mandatory for production-grade agentic systems where reliability matters more than local convenience. The decision to scale inference workloads on consumer-grade GPUs requires a reevaluation of default memory utilization parameters before attempting any serious deployment because the hardware simply cannot support the theoretical capabilities without specific software tuning that many users overlook in their rush to test new models locally. The distinction between your model running and it performing hinges entirely on whether your stack prioritizes theoretical context length over actual token throughput, demanding a reevaluation of every single memory utilization parameter before scaling inference workloads to consumer-grade GPUs. Some users successfully achieve higher utilization via specific tensor parallelism flags or alternative backends, like Llama CPP, that better exploit sliding window attention, suggesting the bottleneck is partly software configuration rather than an immutable hardware limit. But this requires deep technical knowledge most junior engineers do not yet possess when they first start exploring local inference capabilities. Consequently, you must recognize that attempting to run large models on consumer cards without understanding these bandwidth constraints will lead to poor latency and unexpected costs if you eventually move your workloads to cloud environments where those same bottlenecks become financial liabilities rather than just performance frustrations. The path forward requires accepting that theoretical speed does not equal real-world execution when memory bandwidth becomes the limiting factor for data transfer between graphics card central processing unit interfaces. This realization changes how you approach every new model release and forces a more rigorous evaluation of hardware specifications beyond simple video. Random access memory capacity to include aggregate throughput capabilities essential for production-grade applications. Understanding this dynamic allows you to make informed decisions about when local inference is viable versus when cloud infrastructure with higher bandwidth becomes the only option for maintaining acceptable performance standards in your development pipeline. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.